Today, we are going to tackle a concept that sounds, well, complex numbers. But what if I told you the answer to a seemingly impossible math problem wasn't some weird new number, but a whole new dimension? Let's dive in and see how one simple question completely blew up the way we see the world of mathematics.
All right, so before we can jump into that new dimension, we've got to understand the one we already live in, at least mathematically. I'm talking about the world of real numbers. For most of us, this is it, the number line. You know it, you've seen it a million times. It just stretches from negative infinity all the way to positive infinity. And it seems to hold every number you could possibly think of. Whole numbers, fractions, even weird ones like pi. It's a perfect one-dimensional universe. Or is it?
And here's the question that breaks everything. Try to solve this using only the numbers on that line. Go ahead, I'll wait. You can't, right? A positive number times itself is positive, and a negative number times itself is also positive. So there's just no real number that works. This simple little equation has no answer in our universe. It's like a mathematical black hole.
So what do mathematicians do? Well, faced with an impossible problem, they did something kind of amazing. They just invented a solution. They imagined a brand new number, they called it I, and they gave it one simple job. I squared equals -1. And just like that, the impossible was possible.
So let's picture our old number line again. From now on, let's call it the real axis. It's our familiar, flat, horizontal world of numbers.
But wait, where does our new number I live? It can't be on the real axis, we already checked. So let's add a new direction. We can draw a second number line, a vertical one, straight through 0, and we'll call this the imaginary axis. And boom, all of a sudden, our one-dimensional line has blossomed into a two-dimensional world, the complex plane.
And what lives on this brand new plane? Complex numbers. Every single point you see is now a number with two parts. A real part, x, that tells you how far to go left or right, and an imaginary part, y, telling you how far to go up or down. Think of it like a single address in this new, much richer universe of numbers. So now that we have these two-dimensional numbers, how do we actually describe them? What are their key features?
Well, since every complex number is just a point on a plane, we can measure its straight-line distance from the very center, the origin. This distance, its magnitude, has a special name, the modulus. It basically just tells you the number's size.
But a point on a plane doesn't just have a distance from the center, right? It also has a direction. We measure this as the angle it makes with that positive horizontal axis. And this angle is called the argument. So here's the key takeaway. Every complex number has both a size and a direction.
Okay, let's really get into it now, because this is where complex numbers go from being a clever little math trick to something truly profound. This is where you see the real magic of this new dimension.
Think about multiplying on that old boring number line. When you multiply 2 by 3, you're just stretching it to be 3 times farther from 0. It's all just stretching and shrinking along one single line. Kind of limited, right? So, what happens when you multiply on the complex plane?
Okay, this is where the magic happens. What happens if we take any number on the plane and multiply it by I? The result isn't a stretch, it's a rotation. And not just any rotation. Multiplying by I rotates any number a perfect 90 degrees counterclockwise every single time. So just let this sink in for a second. What used to be a simple act of stretching has gained a whole new power. In the complex plane, multiplication is rotation. When you multiply two complex numbers together, you just multiply their sizes, their moduli, and you add their angles, their arguments. This simple, elegant idea changes everything.
And this incredible link between multiplying and rotating, well, it uncovers some of the most beautiful and hidden patterns in all of mathematics, especially when we start looking for roots.
Let me ask you a simple question. What number, when you multiply it by itself 3 times, gives you 1? Well, duh, 1, obviously. 1 times 1 times 1 is 1. And in the real world, that's it. That's the only answer. But what about in the complex plane? Are there others? You bet they are.
And would you look at that? The answer is just stunningly beautiful. The 3 cube roots of 1 aren't random at all. They form this perfect symmetrical pattern, the 3 corners of an equilateral triangle. Each one is a number that, when you multiply it by itself 3 times, rotates you perfectly back to the start. It's a hidden harmony that's suddenly made visible.
Now, at this point, you might be thinking, okay, that's a really neat geometric trick, a cool pattern, but so what? What's the point? And the truth is, this trick is actually the foundation for so much of modern physics and engineering. It's not a game, it's a tool.
I mean, think about it. What other things have both a size and a direction? How about things that rotate or oscillate, like an AC electrical circuit? Engineers use complex numbers all the time to describe voltage and current because their relationship involves a phase shift, an angle. This imaginary math makes it incredibly simple to analyze very real things, from radio waves to the quantum spin of an atom. It unifies algebra and geometry in this profoundly useful way.
And that leaves us with one last, big thought. We started with a simple line of numbers, we ran into an impossible problem, and we solved it by literally adding a new dimension. It really makes you wonder, what other mathematical problems that seem completely impossible today are just waiting for us to find the right dimension to see them clearly?